The idea I'm going to show you now is the fact that the net amount of work that is done to an object is always going to be equal to its change in kinetic energy. Amongst all the types of energy, kinetic is special this way. So let's consider a block. So we have a block, and let's say it's got a mass of 10 kilograms. It's sitting on a surface where the coefficient of kinetic friction is equal to, let's give that 0.5. And we're going to apply a force to this block. And let's give this force a magnitude of, I don't know, let's say 100 newtons. And we'll put it at an angle of incline of 30 degrees. Now, if this is going to continue, and it's going to pull the block for 2 meters, my question to you is, how fast will that block be going after it's gone for 2 meters? Now, we could find the net force, divide that by mass, get the acceleration, drag out our kinematics equations, take that final displacement, and find the final velocity. But that's not what we're going to do right now. I'm going to show you how to find the net amount of work that is done. And that net amount of work is going to be equal to the change in kinetic energy. So if we assume this block started off staying still, we can then easily find its final velocity. Okay, so let's get to work here and find the net work on this. I'm going to draw a free body diagram. We have a 10 kilogram mass, so that means it's got 98 newtons of gravity pulling it down. Also, we are pulling at a 30-degree angle with 100 newtons. So that applied force is going to have an upward component of 100 times the sine of 30. And 100 times 30 sine is 50. So we've got 50 newtons pulling up. Pulling forward, we're going to have 100 times the cosine of 30. And 100 times 30's cosine is 86.6. So if you're not familiar with turning a force into its perpendicular components, I suggest you review that before coming back to here. So what I did was I took this force, this applied force of 100 newtons, inclined at 30 degrees, and I found the vertical component and I found the horizontal component by doing a little bit of trigonometry. If you multiply that by the sine of 30, that gives you the vertical side of this triangle. So that's my vertical component. And if you multiply it by the cosine, it gives you the horizontal component. Okay, we also have a normal force pushing upward on this. Now, the magnitude of the normal force will be such that the net force upward and downward is 0, unless the upward component of that applied force exceeded gravity, but in this case it doesn't. So that normal force looks to me like it's going to have to be 48 newtons, because 48 plus 50 is 98. So we have a net upward and downward force of 0. Let's label it, that's the normal force. This is the applied force along the y-axis. That's the applied force along the x-axis. We're now going to also have a force of friction pushing back. And our force of friction is 0.5 multiplied by the normal force. So our force of friction is going to be 0.5 times 48. So our force of friction, 0.5 times 48, is 24 newtons. Once we consider all things here, the net force on this body is going to go this way, and our net force is 86.6 minus 24. It is 62.6 newtons. with a net force of 62.6 newtons and a body that's traveling, and this part's important here, that net force and the motion are in the same direction, so I can just multiply them. I'm going to have a net amount of work. My net amount of work is going to be equal to the force, 62.6, multiplied by the distance. So it's going to be 120 something. It's going to be 125.2. 125.2 joules. That's the net amount of work done to this body. The net amount of work is the change in kinetic energy. So if I was initially staying still, my kinetic energy was 0, and my change in kinetic energy, so we'll call that the delta EK, my change in kinetic energy is a positive 125.2 joules, then that means that my final kinetic energy is 125.2 joules. So my final kinetic energy, and we know that kinetic energy is half mass times velocity squared. My 125.2 joules of energy is equal to 1/2 of my 10 kilograms of mass times v squared. So that's going to mean that 2 times 125.2 divided by 10 is equal to v squared. So v is the square root of all of that. So my final speed after this block has been dragged forward by that force for 2 meters is going to be 2 times 125.2 divided by 10. We square root all of that, and it is 5 meters per second. It's actually 5.0039. That'll easily round to 5. I didn't intend for it to come out so cleanly. I guess that was just lucky. One thing to consider here is I'm going to just show you a frictionless problem real quick and talk about the dot product. So let me just do one more example before I quit this video. I'll recap that one quick because it's, I guess, good to recap them. So in this problem here, we have a force of 100 newtons, and that 100 newtons is being exerted on a block that has a mass of 10 kilograms. So that 10 kilogram block gets a force of 100 newtons inclined at 30 degrees, and that pulls the block forward over a distance of 2 meters. And the question is, how fast is it going after that? The net amount of work that was done to the block is going to be equal to its change in kinetic energy. To find the net amount of work, I found the net force on the block. That net force was 62.62. Sorry for moving that around. That net force was 62.62. And if we multiply the net force by the distance the block moved, as long as they're collinear, that is, as long as they're moving in the same direction, that gives you the net amount of work. The net amount of work, the 125.2 joules of energy, is equal to its change in kinetic energy. And since it started with no kinetic energy, that ended up being the final kinetic energy. Okay, so let's just quickly consider one more problem here. So we're going to start out again with a block. Now let's put this block on a frictionless surface. So we've got no friction at all. This is a block of wood on ice, and that ice is really smooth. The Zamboni's just gone over it. Block sliding perfectly. And let's say that block has a mass of 5 kilograms, and we're going to pull forward on it with a force of 30 newtons. And our 30 newtons look to me to be inclined at about 40 degrees. Okay, so what is my net work? My net work is going to be equal to that force multiplied by the distance it traveled. Let's say this is going a distance of 1 meter. And it's going to be that 30 newtons multiplied by that distance of 1 meter multiplied by the cosine of the angle in between them. So this is 30 newtons multiplied by 1 meter multiplied by the cosine of 40 degrees. Now what does multiplying by the cosine do? Multiplying that force by the cosine of the angle finds the component of the force that is horizontal. In this case, that's horizontal. That gives us the component of the force that is in line with the motion of the block. And it's that component of the force that contributes to its change in kinetic energy. So I'm going to multiply these out. And 30 times 1, obviously, is 30, multiplied by the cosine of 40 degrees. That gives us a net work of 22.98 joules. That 22.98 joules is equal to our change in kinetic energy. So that means that our kinetic energies change, and if we started out at 0, our final kinetic energy is 22.98 joules. So that 22.98 is equal to half of our mass, which is 5, times the square of our velocity. So we're going to multiply that by 2. So we've got 2 times 22.98 all over 5. That gives us v squared, and if we square root both sides, that's going to give us our final velocity. So our final velocity is 22.98 times 2 divided by 5, and then we're going to square root that, and it gives us a final velocity of 3 meters per second. So to recap the entire video, the net work that you do to a block is equal to its change in kinetic energy. If you've got multiple forces acting on a block, it's convenient to find the net force and then multiply that net force by the distance the block moves, as long as they're in the same direction as one another. If you just have a single force on that block, you can find the component of that force that lines up with the motion of the block by taking the cosine of the angle in between them. The work is equal to the force multiplied by the distance multiplied by the cosine of the angle in between them. That gives us the net amount of work done, which is equal to the change in kinetic energy on our block.